Right, we're going to get started here. Questions before I launch into the very cool Richardson's extrapolation? It is very cool. Any questions? Okay. I'm randomly going to tell you that I had COVID. I got COVID in August, I think around August 12th or something like that. And, you know, I was off, like, kind of sick for about 1 week, and then I was sort of back, whatever. But I have to say, now what is it? End of October, I finally have my energy back to normal. That is a long time, right? I'm like, well, productivity slightly decreased, training schedule out the window. My first did not finish in a bike race, right? And I was like, that is amazing. One little virus, you think it's just, anyway, I find it astounding. Okay, we're going to talk about Richardson extrapolation. We looked last time at the numeric differentiation, and we saw that we can have 2-point or 3-point or even 5-point or 7-point or whatever formulas. And the lower order formulas are a little bit less accurate, but they are more convenient. So the Richardson extrapolation is a way of getting a higher order accuracy out of the lower order formulas. It's almost like you get something for nothing, honestly. It's quite cool. So we're going to assume that we have some number, m, that we want to approximate. Like we could be just thinking of this as maybe that's our approximation for the derivative. And we're going to approximate it with some other function, a quantity, which is a function of h. That is a step size. So again, just thinking of the derivative, that is our distance between the 2 points. And we have the situation, if we have the situation where the difference between the thing we want to approximate and our approximating function, the difference between the two of them looks like this. That was the case for numeric differentiation. If we're in that situation, we imagine the situation where we also compute n1 of h over 2. And so then what I'm doing here is just substituting in h over 2 for h in 1. That's what 2 is. I'm just substituting in h over 2 for h. We recognize from looking at this that this is an OH approximation. This one here is also an OH approximation. And what we're going to try to do is combine these two to get an OH squared approximation. Maybe you can see it immediately by doing that. What you should do is you know, we're going to be doing this algebraically. There's nothing really tricky here. And we take this one, maybe we multiply this one by a half and then subtract one from the other. So we basically want to try to do is eliminate this guy from the thing, because then we'll end up with a OH squared approximation. That's the idea. So if subtract equation 1 from twice equation 2, let's see what happens. So I'm going to take twice equation 1, that'll be 2m minus 2n1h equals to 2c1. Equation 1, subtract, hang on, I'm starting again. I'm going to take twice equation 2. I started writing equation 1. I'm going to take 2 times that guy. 2m minus 2n1 h over 2 equals 2c1 plus c2h squared over 2 plus c cubed h cubed over 4. Multiply both sides by 2. Okay. And then I'm going to write the other equation below. M minus n1h equals 2, I forgot the h, 2c1h plus C2H squared plus C3H to the 4. Okay, and then I'm gonna subtract and solve for M. So I subtract, I get M, and then on the right-hand side, I'm gonna get what? The N1. Oh yeah, I get 2 N1H over 2 minus plus N1 of H. Which way am I subtracting? I want to make sure I'm subtracting the right way. There. Minus C2 over 2H squared minus 3C3 over 4H cubed. Now I'm still trying to approximate this guy. That's what I'm starting to approximate. Now I'm going to approximate it with this. 2 OH approximations, but my combined approximation is the first term that I'm going to truncate is OH squared. So my new approximation, which I'm going to call N2, is going to be 2 times N1 H over 2 minus N1 of H. And it's an OH squared approximation. Don't need to invent a new formula. I don't need to look at something like that. I'm just gonna use it, the distance H on function evaluation, the distance H over 2 function evaluation. I'm going to combine those in a smart manner, and I'm actually going to get an increase in accuracy and OH squared approximation. That is the idea of this whole thing. Okay, we can just keep doing this. Suppose we want an OH cubed approximation. We've already got N2, which is a OH squared approximation, and we have the remainder term there. We do exactly the same thing. We replace this H by H over 2, and then we subtract one from the other in order to get cancellation on this guy. And in order to do that, you have to subtract 4 times. You take this one, you multiply it by 4, and then you subtract this one. Let's see, I'll do that. I'm going to have 4m is then going to be 4n squared h over 2 plus c2 at h plus c3 at h squared h cubed over 2, and there's more terms. And then I'm subtracting. That's 4 times equation 4, subtracting equation 3. That is this, N2 of H plus C2 hat H squared plus C3 hat H cubed plus dot, dot, dot. And so then I go ahead with that, and I get 3m is 4n2 H over 2 minus N2H plus C3 hat H cubed over 2 minus, actually, I should probably get that next one. C3 hat H cubed. Okay, and that gives you then your next approximation, this thing right here. Okay, so now our next approximation, we're still trying to find an approximation for M. My next approximation that I'm going to say N is approximately, well, I'm going to say M is approximately N3 of H, and N3 of H is going to be 4N2 of H over 2 minus N2 of H over 3. And M is equal to N3 of H plus something, an error term, which is now OH cubed. Yep. other questions? Yep. Okay, so what we're doing is we have something that we want to approximate. We have something M, like let's just call that F planet X, right? We want to approximate that. So we have a method of doing that. That is what we're calling N1 of H. It's our first approximation. Okay, in the case of the derivative, N1 of H would be F at X1 minus F at X0 divided by H. Right, that's our first approximation. Now, rather than increasing the complexity of this, we're saying, no, don't increase the complexity of that. Instead, calculate N1 of H over 2 and combine them to get, so you calculate these two instead, and then you combine them to get N2 of H. And that is a better approximation. Then you can, if you want, you can calculate N2 of H over 2 and combine those two and get N3 of H. And each time you do this, your accuracy goes up. Your first approximation, this guy right here, N1 of H, your first approximation to the derivative was an OH approximation. So is this one, the OH approximation. Then by combining them, you get this guy, which is an OH squared approximation. So it's better accuracy. I mean, the error goes down more quickly as H equals to 0. And then you take those two OH squared approximations and combine them in a smart manner, and you get an OH cubed approximation. You can do this as many times as you want, without increasing the complexity of the way that you're calculating your approximation. We're not changing what we're doing. We're just making the same kind of approximation in a bunch of different places, and then combining them in a smart manner. That's the idea. And you keep going. Okay, I'm going to write the general formula because it's here, but I mean, I would never be able to write this out of my head. I would not recommend this. Remember, I put this on a formula sheet if you want, but I don't even use it. But it is just like this. So this is your J correctly. Like that. So you can just keep generating these things and make sort of like what I just wrote to the side. You do this in a systematic order. You start out with your basic approximation like that. Then you have a additional approximation. And you can have as many of these as you want. And each time you're reducing the step size. And then you combine these two and you get N2 of H. And these two, N2 of H over 4. And these two, N2 or H over 2. N2 H over 2 and N2 H over 4. And then you combine those ones. Let's go into this column now. Combine those ones and you get N3. Combine these ones and you get N3 of H over 2. You combine those two, you get N4 of H. And each time that you go through this process, you get an increase in the accuracy of your approximation. Maybe I will attempt the feat of drawing this out geometrically for the derivative. So you have a function like that. Here's some point on your function, x0, There's some other point in this function. That's wrong. You're attempting to approximate the derivative at x naught. This distance here is h. Your first approximation to the derivative at x naught is this. Right? That is that f prime at x naught is approximately f at x1 minus f at x naught all over h. Okay? That is what in this world is being called n1 of h. Then what you do is you take half h over 2. Like that, h over 2, and you make the same calculation of the tangent line. It's still an n1 approximation. You just use those 2 points. That's what we're doing. That is still, so now that is that blue line is n1 of h over 2. Also in an O, this one is an OH approximation, and this one is also an approximation for f prime at x naught, and it's also an OH approximation. Then what you do is you algebraically do what I did, combining these 2 lines. So you take some amount of that one and some amount of that one, and you get a better approximation. Oh, if you do it in the way that we just went through, you get an ON squared approximation. So what you're doing is you're taking some other line here, like that, which is a combination of those. It's better, the OH squared approximation. Then if you don't think that's fine, then you divide the interval again, and you go h over 4, and you do the whole thing again. So you're using the same type of approximating with different interval sizes, and then you're combining those to get a better estimate overall. That's the idea. It works not just for differentiation, it works for any approximation thing that has the kind of form that we have. Yep. Oh, let me scroll back, where we got the OH2 one. This too? Here? Let's see. I did, I multiplied equation 2. Did I make a mistake? I might have made a mistake. No, hang on. Hang on. I multiplied this equation by 2. I got 2, 2, 2, 2. Right? That's this 2. C1. Oh, yes, this is h over 2. Thank you. And then the bottom one, I subtracted 1. This should be C1. Thank you. That is correct. Now that cancels out properly. I mean, the whole point was for these 2 things to cancel out. They had to be the same. Yep. Good observation. Yep. Algebra meltdown, light algebra meltdown. Okay, so that is what we're doing. We're doing the same thing, but we're doing it for 2 different interval sizes. We're combining those in this method, and then recognizing when we do this one is OH squared. So it's better. Other comments, questions? It doesn't, yep. The last term in this one here. Yep. This one here. And 1H. No, that's just a copy of this, right? Oh, this is the HQ. That's what you're telling me. Thank you. Yep, you are correct. No, you know what's it, you know, I can tell you how this happens, and I have not been able to get it out. My head is what's happening. I'm writing CH cubed, and I'm thinking to myself, the next term is C4H to the 4. And then the 4, right, comes down when the 3. It's that thinking ahead. No problem. What you're trying to write at the same time. Okay, let us see this delightful situation in action. It doesn't just apply to numeric differentiation. It can be done whenever the error term has this format to it. Okay. So for example, if we had something we wanted to approximate, and then we had our first approximation to it, and then the error term looked like this, it is possible to do it. So whenever the error term is looking like that, it doesn't have to be going up like every power. It has to be going up in a regular progression. Okay, this is our point here. This is our truncation error. So we get if we're in the situation where these are 2, 4, 6 rather than 1, 2, 3, we get a different approximation formula. I don't even want to write it down. You can just look into those errors. I'm not going to ask you to write that out. This one here is the center difference formula. The one I did first was for the forward difference formula for the derivative. This one is the center difference formula. We already saw that the center difference formula had a different error profile. It was better. Okay, I'm leaving that like that. Okay, I'm going to give you an example here. With a function, you can actually see the accuracy. Actually, really, I find it really kind of amazing. Okay, so we've got this function f of x. Let's take a nice function here, x e to the x. There. I'm going to take the derivative of this guy. The derivative of that guy is e to the x plus x e to the x. Okay. Now I'm going to let x naught be 2, and my little gap gauge is going to be 0.2. Now I'm going to exactly calculate, best I can with my calculator, f prime at 2. So I'm going to basically be substituting 2 into here. Like I'm doing the actual differentiation, evaluating it at 2. So I get e to the 2 plus 2 e to the 2, and that is 22.167. 168, and there's some other things there. Okay, so this is so I can show you that this gets better. Okay, we're gonna use forward difference method for numerically differentiating, and then we're gonna also then use the Richardson extrapolation and see what happens. Okay. So we are going to calculate N1 of H. This is our first approximation to the derivative. And we do that like this, f at x naught plus H minus f of x naught over H. So let's just go ahead and do that. That's going to be f at 2.2 minus f at 2 divided by 0.2. That's using the secant line to approximate the tangent line. I have the function. I can make those calculations. Do that, and I get this. 25.3846. This is an OH approximation. Okay, you'll notice the difference here. That's my approximation. There's the exact answer. And it's not completely desperate, but I'm hardly really good. Now I am going to calculate N2 of H. N2 of H is 2 N1 of H over 2 minus N1 of H. Already calculated. So I'm going to calculate then N1 of H over 2. What is that? That is F of what? Pardon? 2.1, absolutely, right? H is 0.2, H over 2 is 0.1. I'm taking F of X naught, 2, plus H over 2 is 0.1. That is there, and then that's minus F of 2, and then this is 0.1. That is the same calculation, just done when H is half the size. I get a number. It's 23.7084. I mean, it's somewhat unsurprising in that we've decreased the size of H. We've gotten a better estimate, but that's not totally where this is going. What I'm now doing is saying, I'm not just gonna say, oh, I calculated N1 of H, and then I made the interval a little bit smaller, and I got a little bit better of an estimate. No, that is so far what we did up until we learned about Mr. Richardson. Now that we know about Mr. Richardson, we're like, hey, we can do better. We're gonna combine those two things in this manner. I'm gonna take 2 times N1 of H over 2. That's this number right here. 23.7084. And I'm going to subtract from that my original estimate, that guy right there, 22.167. And I get 22.0322. This is an O H squared approximation. And look at how much better it is. Look at how much better it is. For almost nothing. I just had to do the same thing twice, and then you can buy it and tell it. If I had to do that one, then I would continue with the plan and go to the next one. Yep. Which one did you think I didn't? Oh, yes, I put the exact value in there. Thank you. Copying error. 25.3846. Absolutely. That needs to be the exact. That needs to be this approximation, not the exact value. Yeah, we don't know the exact value here. We have that. I mean, we wouldn't be approximating if we knew the exact value. So yes, you're right. Thank you for noticing that. Copying problem. Absolutely. This is N1 of H right here. N1 of H. How cool is that, right? Okay, so there is a file in Canvas, rich demo, and we've got a function here, and we're calculating the derivative at 0.09, and then we did a thing. You can run the program and see this, but you'll see that the actual answer. Where's the actual answer? Here, I'll put the actual answer. F prime at 0.09 is minus 14.2321. So now we start our numeric differentiation procedure, and really it is the pitch, right? Our first approximation to something that is minus 14 is 20. Okay. That is because the sine function is sine of 1 over x is oscillating quickly. And if you pick two numbers and they're, if you're trying to estimate a derivative and you pick two numbers, say you want the derivative here, and you happen to pick this number and this number, well, that would actually work quite well. But if you happen to pick this number and this number, rather than estimate the derivative to be 0, you're going to estimate it to be a very large positive number. So if you have a lot of oscillating in your function, then it is difficult when you pick the numbers. Okay, so if you proceed with this program of the Richardson extrapolation, though, I'm claiming, and you can run the numbers to show me that the initial approximation is really bad, but we don't give up. We do 4 steps of the Richardson approximation, and we find that the difference between the actual derivative and the fifth Richardson extrapolation formula is already down now to 1.821 times 10 to the minus 12. It's massive improvement. Gone from something that's actually useless to something that is useful. Okay, it's a super powerful tool. It's going to come up again when we do the Romberg integration. This is the guide, and you can use it for more than just this. All right, question. Oh, here, you're wondering if there should be an inequality or not? Yeah, so in this case, because I know what my approximation is and I know the exact value, I can tell you exactly what the error is. Normally, when we're approximating stuff, we don't actually know what the exact number is, wasting time, right? So then in that case, we have a bound, but in this case, it's exactly what the error is. Yep. Oh, yeah, well, yeah, yes, so, yes, that's right. We in this model, what we're doing is we're just showing that as we're going along, we're getting, we're going from OH to OH squared, whatever. But if you recall, when we did the numeric differentiation, we actually did have we had a type of a bound, right? Which was a bound on the truncation error. So we actually can bound it. But the problem with that was that if we tell you an error bound based on the truncation error, and then you're like, oh, I see the truncation error depends depending on H, and so I'm going to make H small. Then we showed, like, from a computational perspective, when H is small, you start getting amplification of round off error, and that is dependent on your function. And you can't in this way bound the error like you'd like to be able to say, here's how you bound the error, and here's what you do to reduce it down to below whatever it is that you want. You can't do that in this case. You're like, you got 2 types of error and they play off against one another, but it is the case that those constants are known for the truncation. Just like I didn't bother writing about all. It's just captured the C and C1 half. That's what it's. Yes, that's right. Yeah, that's correct. Yep. Yeah, good question. Other question. Okay, let's move to our that's it about numeric differentiation. Really, having a whole lot of tactics, right? Centered forward and backward and centered 2-point formula and 3-point formula. That's it. Yeah, this method of increasing the accuracy. Okay, now we're going to move to the next topic here, and that is numeric integration. This is a much bigger issue, but it's easier. You can bound the error in this case. We don't have that problem like we had with differentiation, and numeric integration is a hugely important topic used all the time. Okay, so we are going to use the word quadrature. We call this numerical quadrature. This comes from, the terminology is coming from, maybe I'll even just draw this out. You may have not thought of it this way before, but let's look at the handy dandy Pythagoras theorem, right? We say this. C squared is equal to A squared plus B squared. That's the Pythagorean theorem. And we tend to say it like this. And you'll notice that when we use this, we say C squared. We generally don't say C to the power of 2, right? And when we say this, we say C cubed. We don't say C to the power of 3. But as soon as we go to here, we stop with that little program and we go C to the 4. And thinking back to this thing here, the actual thing is telling you that the square, let's look at this length, the square, the area of the square on the hypotenuse is equal to the area of the square on the two sides. Right? This area plus this area is this area. It's about area. And it's about the area of the square, which is why we call this the square. This is why we're calling this quadrature, which is making the equivalent of like squaring the circle, which means, can I find a square that is the same area as a circle? You have a circle like that, and then you say, can you square the circle? And it means, can I find a square that has the same area? That is the square and quadrant. So this is what where this terminology is coming from. For the record, can we square the circle? If I give you a circle and draw a square, that's the same area. Can you do it or not? Not do it. Is this possible or not possible? Huh? Someone's going with the impossible. Yep. Exactly. Right. This is a big thing. I mean, the Greeks spent a lot of time trying to square the circle. Right. They didn't know that pi is transcendental. They didn't have that concept. Right. They're like, there must be some square. They keep trying to find it. That didn't work. Right. Then you have to go, oh, something happening here that I'm not aware of. Anyway, the point is that you are here talking about areas. If you're thinking about it this way, not algebraically the way you think of it here. Okay, so this is what it is, numerical quadrature. The idea is to approximate the area of something in a certain manner. So for us, that's mostly going to be saying we have an integral from a to b of f of x dx. This a definite integral, that is the area under f of x. We're going to approximate it with some type of sum. Right? We're not going to actually perform we're not going to figure out what is that function at all. We're just going to use the function that we have, and we're going to approximate it. So once we made this decision that we're going to approximate an integral by a sum, we have two choices we can make. We can decide what constants we should use, and we can decide what nodes we should pick. Try to make the approximation good, which means accurate. Okay, so both the weights and the nodes might be able to be chosen. Sometimes these are fixed by the experiment or something that you're running, but if they're not, then you have the ability to choose AI, the AIs and XIs. Okay, so the idea is to take this function, interpolate it with a polynomial. How about that? And then integrate the polynomial instead. So we are going to go through, you will likely recall with delight and joy, the trapezoidal rule from calculus 2, right? Somebody told you what this was, right? And it's not that complicated. You have some function like that, and you're like, hey, I got a good idea. I'm gonna just draw a trapezoid here. I'm gonna tell you that's the area. That's the trapezoidal rule in a nutshell, right? And that is what it is, and that is how it may have been explained to you, and then you're given a formula. Or you can derive the formula, and we don't talk about the area. So, okay? That's the calculus 2 model. Now what we're going to do is we're going to start with the Lagrange linear interpolating polynomial. Then we're going to derive the trapezoidal rule, and we're going to do that so we can get a bound on the error. That's where that error formula, in the Stewart textbook, error formula for trapezoidal rule is, error formula for midpoint rule is, error formula for Simpson's rule is, and you think to yourself, please let me get that on the formula sheet, or I hope that I don't have to memorize that, right? Okay, so now after this, you'll be able to say, hey, if I ever forgot that and really wanted to know it, I could start with my the Lagrange interpolating polynomial, and I could derive the error formula. It's not coming from nowhere. Okay, so that's what we're going to do. We have a function under which we want to find the area. We are going to interpolate that with a linear polynomial written in the Lagrange format, looking like this. Copy this out, trying not to make a mistake. There, that's the linear Lagrange interpolating polynomial. We know from having spent a bunch of time with this that our function can be represented by that polynomial plus an error term that looks like this. This is the error in the linear Lagrange interpolating polynomial. This is an exact statement, right? If I know this exactly, like this is a strict equality. If I know that thing exactly, then I know exactly what is f of x. Okay, we're going to be using p of x to approximate. Okay, so now what I want is the integral from a to b of f of x. So I integrate on the other side as well. I'll get the integral from a to b of p of x dx plus 1/2 the integral from a to b of f double prime psi of x minus x naught x minus x naught dx. Like that. This here is my approximation. This here is my error term. Okay, let us do the integral, this integral right here. The integral from a to b of the p of x dx. That is, I'm integrating this. Not that bad, right? I mean, x is a variable, it's like that. The rest of the stuff is numbers. It's not bad, and that looks like this. X minus x1 squared over 2 times x naught minus x1. Okay, f at x naught plus x minus x naught squared over 2 times x1 minus x naught times f at x1. Okay, is that reasonable? Is that integration there? That is going to be, it's a definite integral, is going to be evaluated at a and b. Okay. If x naught minus x1 is equal to 8, then this thing becomes h over 2 times f at x naught plus f at x1. Okay, voila. Coming from the linear Lagrange interpolating polynomial, and in high excitement, I now can think about this in a manner that's going to allow me to bound the error. Okay. We use a theorem here just to basically, the theorem is stated here in the fib, is just so that we can claim that this does not change sign on the interval. Use that theorem, and so then we can write out what the error is. The error as a function of x is 1/2. That's what I have written above here. Integral from a to b, the second derivative, evaluate psi of x. This is going to get us on the back. And I am going to use this thing right here to say there's some number, C, where that's going to be maximum. I'm going to pull that out. It's just a number. And I've got this integral. There. I'm just going to say C is some number and x naught, some number. Okay, I go ahead and integrate. Not too bad. Do that integral. I get this 1/3 x cubed minus 1/2 x squared x naught plus x1 plus x naught plus x1 x naught x1 x. And I'm going to evaluate that at A and B. And then this is really x naught and this is x1. So I've only got 2 points. And I get here minus h cubed over 12. Second derivative. There. Now I have an error bound for the calculator. Written down here. There it is. So you can take an integral. You can approximate the area by a trapezoid over the whole interval, and then your error will be h cubed over 12, second derivative of something. This is some number, whatever number. There you go, it's OH cubed method. And we already saw graphically what that looks like. We have a function, and what we're thinking of doing is making one trapezoid over the whole area that we want. And we can, I think in calculus 2, we did a situation where we're like, hey, let's go in like this and make a bunch of different trapezoids. One in each interval. Simple. Okay, are there questions about this? One of our, yep. So one of our most basic methods of estimating the area on the function. Okay, I'm going to say one final thing here, and then we will pick up back with this on Friday. That is our next foray into doing this is Simpson's rule. Who can tell me what Simpson's rule is? So I'm trying to estimate some function, the area under some function. It looks like that. And instead of drawing a straight line through it, the trapezoid rule, I'm going to do something else. I'm going to use 3 points. Think about this. I'm going to use, you knew that as soon as I said that, right? I'm going to use 3 points, and I'm going to put a polynomial through 3 points. If it's going from 2 points, next obvious thing to do, 3 points. 3 points, polynomial going through that is a quadratic. So I'm like, okay, I'm going to take the area here. There. That's going to be my next estimate. You do exactly the same thing and derive the formula for Simpson's rule and get an error bound on Simpson's rule. We will do that on Friday. Thanks, guys. I will see you then.